Some things are harder to stop than others. Momentum is a way of measuring how hard something is to stop. In this video, I'm going to take a look at how to calculate momentum and the rules around these calculations. We'll discover along the way just how powerful this theory really is. The faster something is going, the harder it is to stop. The more mass something has, the harder it is to stop. So momentum depends upon mass and velocity. We write the equation as P equals mv. We have to use P for momentum. We can't use m because m is mass, and that would be very confusing. The Latin word impetus sort of loosely means momentum. We can't use I because I is the symbol we use for inertia. As we said, we can't use m, so we use P. This equation is actually quite straightforward, so let's jump straight in with an example. What's the momentum of a charging rhino if it has a mass of 750 kilograms and a speed of 12 meters per second? We start with the equation P equals mv. We then put the numbers in. The mass is 750, the velocity is 12. Multiplying those together, we get 9,000. The units are kilogram meters per second. That's because it's mass, which is kilograms, times velocity, which is meters per second. So it's kilograms meters per second. So we can find the momentum of a moving object. If it's not moving, it doesn't have any momentum. The real power and beauty of using momentum comes from the conservation laws. Before we look at that, can I just point you in the direction of my website, which has several free resources, including some questions and worked answers to go along with this video. I also offer one-to-one lessons for A-level and GCSE Physics students on a topic of your choice. I also do classes for up to 6 students, and a place in one of those classes is very affordable. I enjoy making free resources, but I can only do that with your support, so please do take a moment to like, subscribe and comment. In any collision or explosion, momentum is always conserved. That means the total momentum before a collision or explosion is exactly the same as the total momentum after a collision or explosion. That's provided that no external forces are acting, which is what we call a closed system. Let's look at 3 examples of collisions and explosions. Firstly, here's 2 balls rolling together with the same speed. What will happen when they come together? See how they are travelling in opposite directions. That's important because velocity is a vector. One of them must therefore be positive and the other one negative. That means the momentum of one of the balls is positive and the momentum of the other one is negative. That makes momentum a vector too. That's very important. The plus and minus signs are very important with momentum. If we add the total momentum before the collision, we get mv for the momentum of one of the balls plus minus mv for the momentum of the other ball. And obviously we add those together, they've got the same speed, the same mass, that equals 0. We can simplify that a bit and say mv minus mv equals 0. Thinking about our momentum law, if the total momentum before the collision is 0, then the total momentum after the collision must also be 0. 2 possible outcomes spring to mind. Firstly, the 2 balls stick together. If they did so, to make the total momentum 0, they would have to be stationary. In the second instance, the 2 balls bounce off each other and head off back in opposite directions at the same speed they started at. In the first instance, all that kinetic energy is lost. They're now stationary. We call that an inelastic collision. In the second outcome, all the kinetic energy is conserved. We call that a perfectly elastic collision. Of course, there's many other possible outcomes where some of the kinetic energy is lost. Maybe in the future I'll make another video on elastic and inelastic collisions. A second example. Here's a stationary bomb. It's stationary, so there's no momentum whatsoever. After it explodes, there must therefore also be no momentum. If we added up all the momentum of all the parts after the explosion, then the total momentum would all add up to 0, because they'd all cancel each other out, going in opposite directions. Here's a third example, and for this one we're going to do a calculation. 2 trolleys A and B collide on a track. They stick together, so what will be their speed after the collision? Well, using the conservation of momentum, we say the total momentum before the collision equals the total momentum after the collision. So before the collision, the momentum of A plus the momentum of B must equal the total momentum of A and B after the collision. I've kind of written this in a way where I've added some A's and B's to try and suggest which m's I'm talking about and which v's I'm talking about. So I've written down a calculation. The momentum before the collision is the mass of A times the velocity of A plus the mass of B times the velocity of B. The momentum after the collision is the mass of A and B, because they're stuck together, times their velocity. Putting some numbers in, we get 1.5 times 5 plus 2 times 3 equals 1.5 plus 2 for the total mass times V. If we simplify that, we then get 7.5 plus 6 equals 3.5 V. Simplifying it even further, we get 13.5 equals 3.5 V. We now move the 3.5 over to get the V on its own, and we get 13.5 divided by 3.5 equals V, and that equals 3.9 meters per second. The trolleys may not necessarily stick together, so there's other possible outcomes for this collision. Following the same method, i.e. the total momentum before equals the total momentum after, will always lead you to the correct solution. There's many other ways that we can apply this conservation law, and that's what makes it so powerful. Keep practicing questions like the ones linked in the description, and I'll see you next time. Maybe now you could watch this. Or is it that? There, that one. Or that one. I don't know. Watch one.